So now in chapter 2, we're going to be looking at finite dimensional vector spaces. This is the first section of chapter 2. Here I have three shapes, a square, cube, and a tesseract, all different dimensional, right? 2-dimensional, 3-dimensional, 4-dimensional. But in this particular section, we're going to be looking at span and linear independence. And just as we do in other sections, we will start by defining some concepts, first thing is a linear combination. So the definition of a linear combination says a linear combination of a list V1 all the way to Vm of vectors in V is a vector of the form A1 times V1 plus dot 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 all the way to AM times Vm. And those A's are elements of F, meaning they're pretty much scalars. They are scalars. That's what a linear combination is. And you might have seen this if you've taken a matrix algebra course or a beginner's course in linear algebra. They have to do with, well, systems of equations. They're some kind of linear combination. And we're going to explore some properties. Before we do, we're going to look at this example. So in F3, 17, -4, and 2 is a linear combination. That vector is a linear combination of this vector here, this vector. And why is that? Well, because 17 is equal to 6 times 2, -4. Oh, sorry, not 6 times 2. We still have to add what's over here. 5 times 1. Over here, -4 is 6 times 1 plus 5 times -2. And 2 is equal to 6 times -3 plus 5 times 4. So notice here, this 6 is an A as a scalar, so is this 5 over here. And in parentheses, we have our vectors. So this vector is a linear combination of these other two vectors, this one and this one. So that's an example of a linear combination in F3. I'm going to go ahead and delete that, so if you need to copy that down, go ahead and pause the video. So I'm just going to erase this really quickly, just to make space. But with linear combination comes another term, which is a span of a set of vectors. So the set of all linear combinations of a list of vectors v1 all the way to vm in V is called the span of v1 to vm. We denote it like this. We just put span in parentheses, the list of vectors. So in other words, the span of all these vectors is equal to all their possible linear combinations as a set, right? And again, A1 all the way to AM, they're all elements of F. And we define the span of the empty list to be 0. And another little example here, we have, so looking at this example up above, we know that this vector here, 17, -4, 2, is in the span of these two vectors. Why is that? Well, because if we get a linear combination of these two vectors, we can get this other vector, right? So it's in the span of those two vectors. Oh, so there's a theorem. But before I even read the theorem, I should mention here 17, -4, and say, let me think about this really quickly, and 5 is not in the span of those two vectors. And why is that? Well, just as I did up here where I had the systems of equations, there isn't a system of equations such that I can multiply a1 times this first vector and A2 times the second vector such that it gives me 17, -4, and 5. That's why this vector, 17, -4, and 5, would not be in the span of those two vectors. So with that said, we can move on to our theorem. The theorem says the span of a list of vectors in V is the smallest subspace of V containing all the vectors in the list. So we're essentially going to prove here that the span of the list of vectors in V is indeed a subspace of V. Right, so we begin our proof by supposing that V1 to Vm is a list of vectors in V. Right, so first we're going to show that the additive identity is in the span. Why? Well, because we can just put 0 as a scalar for all the vectors in this list, and 0, they equal 0, right? So the additive identity 0 is in the span. Also, we can show that the span is closed under addition, right? So if we were to have this linear combination of the vectors and this linear combination of those vectors, well, we just add the scalars, a1, c1, all the way to am plus cm. And now we just have another scalar times v1, and another scalar times vm, and everything in between. And that's just another linear combination. So the span is also closed under addition. And if you guess the third one, it's that the span is closed under scalar multiplication. And why is that? Well, because multiplying this linear combination here with a scalar, just again, we multiply that lambda scalar times a scalar. We just get another scalar times v1, same thing over here and everything in between. So we just get another linear combination. Therefore, the span is closed under scalar multiplication. Right, so what does that tell us? That tells us that that span is a subspace of V. And why is that? Well, because we just showed the three conditions of showing that something is a subspace, right? Remember the three conditions, the theorem we saw in the last section? We need to show the three properties that the additive identity is in the subspace. It's closed under addition. Actually, I should additive identity, closed under addition, closed under scalar multiplication. Those were the three properties to show that it was a subspace. So we know that span of V1 all the way to Vm is a subspace of V. Right? And now, just as we did in the last section, this kind of concludes one part of the proof. But now we're going to show that each, sorry, not each, that the span of V1 all the way to Vm is indeed the smallest subspace of V containing all those vectors V1 to Vm. So first, each Vj is a linear combination of V1 all the way to Vm. And why is that? Well, again, because we can just set any Vj, say V1, right? We can set its scalar, V1, we can set its scalar, Aj, equal to 1. And all the other, this should be A1. Let me erase here. We can set the scalar for V1 to A1 equal to 1, and all the other ones, A2 all the way to AM, equal to 0. Similarly with V2, V3, all the way to Vm. So that's why each Vj is a linear combination of V1 all the way to Vm. Therefore, the span of V1 all the way to Vm contains each Vj. Right? So now conversely, because subspaces are closed under scalar multiplication and addition, Every subspace of V containing each Vj also contains a span. So what does that tell us? Well, that gives us our conclusion that the span of V1 all the way Vm is the smallest subspace of V containing all the vectors V1 to Vm. And now we're just going to add a letter to span to come up with a new definition. So our definition says if span of V1 all the way to Vm equals V, we see that those vectors V1 to Vm spans V. Right? So if V, I can give you an example. Maybe, actually, you know what? I think we have one here. So suppose x1 all the way to xn is a vector of fn. Well, then we can just make uh, x1, just as we did over here, a scalar. It's just a number, right? An element of f, I should say. x2 all the way to xn, that same scalar or number in our list, x1 all the way to xn. And then we make a linear combination using these vectors. One in the first spot for x1, one in the second spot for x2, and then one in the nth spot for xn, and everything in between. What does that linear combination give us? Well, this, right? This vector that we're looking for. So there's a linear combination using this vector, all the vectors in between, and this vector. All those make up x1 all the way to xn, which make up all the vectors in Fn, all the elements in Fn. So any vector x1 to xn is in the span of all these vectors that we used to make that linear combination. I guess I can give you an easier example. The plane, you have the x-axis, y-axis, are 2, right? And the vector 1, 0 and 0, 1. With a linear combination of these two, we can make any element of R2. So for example, of R2, if just pick an ordered pair, let's say 4, 5, we can just make A1 equal to 4, A2 equal to 5. And now we have that 4 times 1, 0. Four, 5. So these two vectors, this vector and this vector here, 1, 0 and 0, 1, span R2. That's what I showed up here, but a more general example, spanning all of Fn and using this exact same reasoning, the same concept. Okay, I'm just going to erase here to make a little space. Sorry if I erased too quickly. You can go back, maybe pause the video if you want to copy anything down. Okay, now we're going to define what I said this chapter is all about. It is finite dimensional vector spaces. So a vector space is called finite dimensional if some list of vectors in it spans the space. Right? And remember, by definition, lists are finite. Right? By definition, every list has a finite length. And now we're going to define something that should not at all be new. You learned this maybe even since elementary school, if not middle school. Sorry, I should mention P of F. This is how we denote the set of all polynomials with coefficients in F. But here's the definition of polynomial. So again, nothing new. A function P from F to F is called a polynomial with coefficients in F if there exists A0 all the way to AM of F such that P of Z is equal to this linear combination for all z and f. And with the usual operations of addition and scalar multiplication, P of f that we have here is actually a vector space over f. And you could very well verify that. It would be a good exercise. P of f is also a subspace of f to the f. Right, the vector space of functions f to f. P of f is a subspace of that. Right. And one last thing I should know, or I should mention, is that the coefficients of a polynomial are uniquely determined by the polynomial. So we're going to define this definition, degree. And well, before I do that, I should mention the polynomial that is identically 0 is set to have degree negative infinity, but let's not look at that yet because we haven't defined what a degree is. Right, so a polynomial, P of the set of polynomials, is said to have degree m if there exists scalars a0 to am of f with am not equal to 0, such that this polynomial is equal to this expression for all z and f. If p has degree m, we write degree p equal to m. So what does that mean? A degree of a polynomial is basically, in loose terms, the exponent, I should say the biggest exponent, right, m. So given polynomial x cubed plus x squared plus 4x plus 8. The degree of that polynomial would be 3. Right, so that's all a degree is, the degree of a polynomial. Now we can take a look at this little note. We define that the polynomial 0 has degree negative infinity by definition, just defining that. Okay, and another definition. For m, a non-negative integer, Pm of f denotes the set of all polynomials with coefficients in f and degree at most m. So it could be less, but it can't be more than m. It can be equal to m or less. Right? A polynomial with degree at most m. That's what this notation means, or that's what this means, that definition. And finally, a vector space is called infinite dimensional if it is not finite dimensional. Okay, in this next slide, we're going to actually start a bit out of order. What I mean by that is we start with the, if you know, the light blue box. Usually we use it for proofs. And the reason is we'll see. I'll definitely mention the theorem, but we'll see why I'm going to go through the reasoning first. So suppose V1 through Vm are elements of V, and that V is in the span of all those vectors, V1 through Vm. Well, by definition, since V is in the span of those vectors, there's a linear combination over here such that that equals V, that linear combination. Now the question is, are these numbers, A1 all the way to AM and everything in between, are those unique? Are these numbers unique? Well, oh, there you go. There's a question. Are those unique? Well, let's see. Let's suppose C1 to Cm is another set of scalars. such that we can find another linear combination that also equals V. Right, so we have one linear combination, I'm going to circle in green, that equals V, and the other linear combination that also equals V. Now, are A1 and C1 always equal? Are they never equal? Are they, right? So that's what we're going to look at. So subtracting the two equations, V minus V, we get 0. And then we just get A1 minus C1 all the way times V1 plus all the way to AM minus CM times VM. Right? So we have written 0 as a linear combination of V1 all the way to Vm. Right? And if the only way to do this is the obvious way, which is using 0 for all the scalars, then AJ minus CJ equals 0. Right? Which will just means that AJ equals CJ, meaning that they're the same thing. And thus the choice of scalars was indeed unique. Right? So this situation is actually so important that we give it a special name. And we're going to define that. So a list V1 all the way to Vm of vectors in V is called linearly independent if the only choice of A1 to Am of F that makes this linear combination equal to 0 is only if all the scalars are indeed 0. So if the only way to write 0 is by having all the scalars equal to 0, then it is we say that those vectors V1 to Vm are linearly independent. And now we can finally state the, again, before we move on, the empty list, we also define it to be linearly independent. But now we can state the theorem that came with the proof. So V1 to Vm is linearly independent if and only if each vector in the span of those vectors has only one representation as a linear combination of the vectors V1 to Vm. And again, the proof for that theorem is the reasoning we used over here. So that reasoning shows, that each vector in the span of vectors V1 to Vm has only one representation as a linear combination of those vectors. We're going to be looking at examples for linearly independent. So these three vectors are linearly independent, but they don't span F4. And I guess little example would be you can't make this vector the vector of all ones in F4 with just using a linear combination of these three vectors here. You can't do that. You can try it out if you like, or you can just believe me for now, because we're going to be dealing with something of that similarity, or yeah, something to do with that soon. Now the list 1, Z, all the way to Zm, so it's just all Z with degree 0, Z degree 1, ... all the way to Zm, is linearly independent in the set of all polynomials of F for each non-negative integer m. And I know you're used to seeing polynomials with x. In this case, we're just using z. You should be comfortable with using different variables. But now we can state what linearly dependent means. So a list of vectors in V is called linearly dependent if it is not linearly independent. So in other words, a list V1 to Vm of vectors in V is linearly dependent if there exists A1 to Am in F, where they're not all zeros, such that this linear combination is equal to 0. Now that may be a bit hard to grasp, so we're going to just look at an example. So this list of vectors, first vector, second vector, third vector, is linearly dependent in F3. Why is that? Well, because we use scalar 2, scalar 3, and scalar -1 times their respective vectors. And again, so for example here, 2 times 2 is 4, plus 3 times 1, which is 3, plus -1 times 7, which is -7, that equals 0. Same thing for the second and third component. So again, this linear combination just showed us that we got the 0 vector without having to use 0 scalars for all the scalars. Therefore, we know that those vectors are linearly dependent. And in some vectors, if some vector in a list of vectors in V is a linear combination of the other vectors, then the list is linearly dependent. And try to think of why. Why is that? Okay, we're going to move on to something pretty big in linear algebra. But it's really known as a lemma, and it's a linear dependence lemma. And what does it say? It says, suppose V1 to Vm is is a linearly dependent list in V. Then there exists J to be 1, 2, all the way to M, such that the following hold. Vj is in the span of V1 all the way to Vj minus 1. And if the jth term is removed from V1 to Vm, the span of the remaining list is equal to V1 all the way to Vm. So it is equal to that span if it is that we remove that jth term. And again, something really important I should note here. We're dealing with a linearly dependent list in V, not independent, dependent. Now we can move on to the proof. This is a pretty lengthy proof, so bear with me. Okay, well, because the list V1 to Vm is linearly dependent, as I just pointed out, there exist these scalars, A1 to AM, not all 0, such that the linear combination can equal 0. And again, we saw that from the last slide. This just comes from being linearly dependent. Well, we're going to let J be the largest element of 1 to M, such that AJ is not equal to 0. Right? Well, what can we do? Well, we can just get that vector Vj. And as you can imagine, it would have probably been like this, but we got this scalar. That's what the last line told us. As long as it's not 0, we got that scalar, and we divided all the terms by that scalar. And then we moved all the terms to the other side, so that's why it's negative and negative. And now, what do we have? Well, this vector Vj is a linear combination of all the other vectors V1 all the way to Vj minus 1, which is what we're trying to show for A. Right, so that proves A. Now, to prove B, suppose U, the vector U, is in the span of V1 all the way to Vm. Well, if that's the case, well, then we can just get a linear combination such that these C1 to Cm are an F that equals U, right? So again, because it's in the span, we have a linear combination that equals U. Right? So using the equation above, this equation here, I'm going to circle it in green, yeah, circle it in green here. Using that, we can replace Vj with the right side of the equation. So, oh, it just said B, thus B holds. But what we're doing is we can just get, let me make this clear. So let me erase here to make this clear. In the equation above, meaning this one here, we can replace Vj. So this Vj over here, I'm circling in orange, we can replace it with this here. And now what does that show? I'm just going to write it out just to make things clear. CMVM is equal to negative A1 AJ V1 minus. So what I did was I replaced this Vj over here that I'm circling with this linear combination. And now it shows that since this is equal to U, well, U can also be written as a linear combination of V1 all the way to Vj minus 1. And therefore proving B. Okay, but again, these slides only include a theorem and a proof because they're really important. And this one is probably the lengthiest of those. So if you need to pause, take a break, something, we're going to go ahead and state this theorem. So the length of a linearly independent list is less than or equal to the length of the spanning list. Right? So in a finite dimensional vector space, the length of every linearly independent list of vectors is less than or equal to the length of every spanning list of vectors. And really, that should make intuitive sense. But we can't just go on and say that it makes intuitive sense and not prove it, right? So we're going to go ahead and prove it. So suppose first that u1 to um is linearly independent in V. Those vectors are linearly independent. And suppose also that w1 to wn spans V. What do we need to show? That m is less than or equal to n. It's referring to this m is less than or equal to this n. And we're going to do that through the multi-step process described below. And we need to note that in each step, we add one of the u's and remove one of the w's. That's what's going to happen here. So as you can imagine, step 1, remove a u. Sorry, add a 1u and remove a w. So if we let B be this list that spans V, well, if we add a vector to that, adjoining any vector in V to the list is now going to produce a linearly dependent list, right? Because all those vectors already span V. So it can make any vector in V. So just adding another vector, well, we can just, make it, I guess, produce that vector with the linear combinations of W1 to Wn, therefore making the list linearly dependent now. Right? So, in particular, the list U1, W1, all the way to Wn is linearly dependent. Again, because that list was already linearly, is linearly independent, or at least it spans V, I should say. So adding the U1, well, we can get that by just making a linear combinations of all these other vectors. Therefore, it's linearly dependent. That list is linearly dependent. And by the linear dependence lemma that we just went over last slide, we can remove one of the w's so that the new list of B of length n, so this here is of length n plus 1. But if we remove one of the w's somewhere in here, or w1, wn, consisting of sorry, we can remove one of the w's so that the new list B of length n, consisting of u1 and the remaining w's, spans V, right? So now we can get u1, let's say we took out w2. So w3, w4, so on and so forth, all the way to wn. Now this is again of a list of length n, which is why it says of length n, that spans V. And why can we do that? Again, because it's guaranteed by a a linear dependence lemma. So that was step 1. Now we can move on to step J. Well, the reasoning for step J is basically going to be the same. The list B of length n from the previous step spans V. Just as we did over here, we removed the W, but we added a U, and it still spanned V because it's guaranteed by the linear dependence lemma. So we can do that over and over again, right? So adjoining any vector to the list produces a linearly dependent list again, but then removing another W will now make it of length n again. And we added them in order, so u1 first, as we did up here, then u2, so that's why uj, we adjoin it after uj minus 1, and we get that linear dependence. And by the linear dependence lemma, just as I said, one of the vectors in this list is in the span of the previous ones. And because u1 all the way to uj is linearly independent, right? Because if you look up here, I'm going to do it in blue. We assumed here that this was linearly independent in V, u1 to um. So u1 to uj is linearly independent. So one of the vectors we remove is one of the w's, not one of the u's. And we can remove that w from B so that the new list B of length n, consisting of u1 to uj, and the remaining w's span V still. After step M, we have added all the u's, and that's where we terminate the process. That's where the process stops. And at each step, as we add a u to B to the list, the linear dependence lemma implies that there is some w to remove. Right? There should still be some w to remove. And what does that show us? Well, that shows it that thus there are at least as many w's as u's. Right? So showing that n is greater than or equal to m, and here n is the length of the spanning list, and m over here was the length of the linearly independent list, thus proving our theorem. One more theorem. I promise it's not as long as this one. It'll be our last slide. And this theorem here tells us that every subspace of a finite dimensional vector space is also finite dimensional. So let's begin our proof. See, it's not that long. So suppose V is finite dimensional and U is a subspace of V. We need to prove that U is finite dimensional, and we do this again, just as we did before, through following a multi-step construction. So last time it was a multi-step process. This is a multi-step construction. So step 1, if U is just a 0 element, then U is finite dimensional and we're done, right? But if U isn't just 0, then choose a non-zero vector, V1 in U. And now if U is equal to the span of V1 all the way to Vj minus 1, then U is finite dimensional and we're done. But if U isn't just that span, well then we're going to choose that vector Vj in U such that Vj is not in the span of Vj minus 1, V1 all the way to Vj minus 1. And after each step, as long as the process continues, we have constructed a list of vectors such that no vector in this list is in the span of the previous vectors. But how do we know that this, I suppose, multi-step construction stops? Right? Well, after each step, we have constructed a linearly independent list by the linear dependence lemma. But this linearly independent list cannot be longer than any spanning list of V, as we saw in the previous theorem. So that's how we can guarantee that this process eventually terminates, which tells us that U is finite dimensional. Not too bad. Luckily, these long proofs are pretty straightforward and not too complicated. I mean, I say that lightly because take that with a grain of salt. I probably had to reread it several times before, I had to chew on it before I actually was able to produce the proof myself. But they're not as hard, I suppose, as later ones. And don't let that scare you, but it just gets more fun.